So it's a really great pleasure to be back here. This is actually my second time at ICTS, and every time I come, it's enjoy it. It's a beautiful campus and it's beautiful weather again. I just came from winter and snow from Denmark, so it's just a big change. But thank you very much for the organizers for having us and organizing this event. So yes, I will talk about group actions, algebraic group actions, where the acting group is non-reductive in general. So the plan is, I will kind of give you a gentle introduction to this theory, mainly focusing on examples and give a broad overview how this developed over the last 12 years or so, when I'm 15. And so in the first talk, I will give you an overview of the construction, how and the background, so about non-reductive group actions and the geometry. Setting up this theory, which we call non-reductive GIT. And in the next two talks, I will talk about generalizations of moment maps from non-reductive group actions and how these quotients can be described using these moment maps as some sort of symplectic reduction quotients. And finally, in the third talk, I will try to give some examples and applications of the theory from the last few years. So that's the plan. So let's start with algebraic groups. So you know that this is an introduction, and I aim to actually also address this talk to students as well, because I know that many students and postdocs are around. So the central problem in geometry, topology, and physics is a kind of classification of objects. And so a moduli problem is about grouping objects in equivalence classes given by a symmetric group, right? And the moduli spaces in algebraic geometry are, how we construct them is very often constructed as quotients of varieties or certain parameterizing spaces by actions of groups, right? So the symmetry is given by a group action, and two objects are considered to be equivalent if they are sitting in the same orbit of some symmetric group action. So in these talks, I will work over C, although probably much of this, what I'm talking about, is works over fields of closed fields of characteristic 0 or even positive characteristic, but I will restrict my talk to C, just to stay on the safe side. Okay, so the observation is that whenever you have a linear algebraic group, G is going to be a semi-direct product of a unipotent group. This is called the unipotent radical of G, and the reductive group, which I denote by R. So, and the unipotent group is the normal subgroup. So the unipotent group is, you can think of that as, and very often we can embed them as a matrix subgroup. So you can think of that as being a subgroup of GLN, consisting of strictly upper triangular matrices. Not strictly, but upper triangular matrices, right? So, and ones on a diagonal. We talk about unipotent groups. And we work over C. That's going to be very important in my second talk and tomorrow. So complex reductive group, there are many different definitions and characterization of these groups. One of them is that it's a complex reductive group is a complexification of a maximal complex subgroup of that. And for example, you can think of the unipotent group sitting in GLN or SUN sitting in SLN. So these are the maximal complex subgroups sitting in a complex reductive group. So we have other definitions, and so one alternative definition is G is reductive. Let's say if every representation of G is a direct sum of irreducibles, right? So it's loosely speaking. Okay, so let's see some examples. And these examples come back later in my talks, especially in the third day when I talk about applications. And somehow these examples served as a motivation and kind of initial starting examples to build the theory. So this is exactly, so let's see some non-trivial examples. So like the automorphism group of a complex projective space, that's kind of, we know that it's reductive, PGLN. But if you take the weighted projective plane, for instance, so let's take P112. So you just take the same quotients, you take just the action of C star on C3, but the weights are 1, 1, and 2, so are not equal. Then we can look at the automorphism group of this weighted projective plane. So I will explain in a second what we mean by that. It turns out it's going to be a non-reductive group. So what is the reductive part? So the reductive is, so let's see what's the, it's going to be a semi-direct product of the reductive part, which is GI2 and the C star. So we'll see it in a second. And then, there is a unipotent subgroup. The unipotent radical is C plus to the cube. So it's an additive group. So what's the action? So imagine that we have these three coordinates, x, y, and z of P112. It has the homogeneous coordinates, but this is a weighted projective plane. So the weight of x and y are 1. The weight of z is 2. So what can we do? We just kind of, the unipotent group, it can add, because the weight of z is 2, is the same as the weight of x squared, xy, and y squared. So we can add, we can take combinations of these three and add to z. So that's something it's allowed as in this space. So that's part of the symmetry group, the automorphism group. So if you want to write down the full automorphism group, you can in a matrix form. You can just, what I put here is P1122. So this is the space of degree 2 polynomials. So it's spanned by x, y, z, and x squared, x, y, y squared. So what you see is that you have this the second symmetric power of GI2, which is just the normal action of the xy coordinates. So in other words, this is the action of GI2 on the degree 2 polynomials in x and y, spanned by x squared, x, y, and y squared. And then there's this extra part. This is the z coordinate corresponding to this column. So we can add some constant times. Is that? Can you hear me? Yeah. Sometimes it's better. Sometimes it's better. Yeah. So yeah, you can add some constant times these first three. So the x squared, x, y, and y squared to the z coordinate. So that's what you can see in the last column. So. But we can see, so this is actually, this picture will come back today, but also later in these talks. So let's see, let me give you like a very short overview of Mumford's classical reductive geometric invariant theory. So this is for reductive groups. So this one is about a complex reductive group acting on a projective variety X. And this requires a linearization or polarization of the action. So we require linearization, which means that we assume that there is an ample line bundle sitting over X, and which results in an embedding of X into the projective space. And there's a lift of the action from X to the line bundle. So this means that we linearize the action. So the action is, if you think of this X sitting in Pn, embedded into the space of sections of L, then we just have, representation of this action as a subgroup of GLM plus 1. So X sits in Pn, it's going to be a linear action as a subgroup of GLM plus 1. And that's this classical picture which we have. So in this case, we have X, and we can take the corresponding coordinate ring of X, which is denoted by AX. So if you think of this X sitting in Pn, it's just going to be given by a homogeneous ideal in this polynomial ring in n plus 1 variables. It's really just the space of sections of L. And the observation is that the quotient space, so orbits, should correspond to invariants of this action on this coordinate ring. So if you form the invariant ring of this coordinate ring, which is AXG, then this is what we call this ring or algebra of invariants. That corresponds, this is a finitely generated algebra. That's a key point. That's where you use this reductive group. It's a finitely generated algebra, so that corresponds to a projective variety. This projective variety, which we call X mod G, that's the GIT quotient of X by G. And this quotient, so this project of the invariants, satisfies certain nice geometric properties. So it's a projective variety, and moreover, if you so let me just come back. So we know that this map from X, this quotient map from X, which sends X to its to X mod G. So it corresponds to the embedding of this invariant ring to AX. That is, if you take the domain of that map, that's what we denote by semi-stable locus. So in geometric terms, it just means that this is the set of points in X where at least one invariant is non-zero. So the map is defined. Then we have this refined picture of this diagram. So we have the original X and the quotient, the GIT quotient, which is project of the invariant. And inside that, there is the domain, right? This is the semi-stable locus where this map is defined. So this is now a well-defined map onto this quotient. And it's a surjection, which is, again, another important thing. So it's a surjection from a semi-stable locus to the GIT quotient. And also, there is an even smaller open dense subset, which is the stable locus, which actually where this map restricts to a geometric quotient, which means that the stabilizers here are trivial or finite, and the points here kind of parameterize the nice orbits, the maximum dimensional orbits of this action. So that's roughly, that's the picture for kind of if you summarizing GIT on one slide, in the next slide I will explain why this is a useful theory. Is the fact that there is actually a way to find these subsets, and this is what we call Mumford criterion in a second. So it's one thing that this ring of invariants is finally generated, but it's not enough. As we will see for reductive groups, in particular unipotent groups, even if the invariant ring is finally generated, the orbit space can be really messy. But the point here is that for reductive groups, this is not the case. So the orbit space is nice. So this means that there is this topological description of the GIT quotient. So it's basically just the S equivalence classes for the points, what we call, after Seshadri, 2 points are equivalent if the closure of the orbits intersect in this semi-stable locus. And so if they intersect, they are mapped to the same point in the quotient. So we only separate those orbits where these closures are disjoint, the semi-stable locus. And so Another alternative description is that we really just describe the closed orbits of the action of G on X. Right, so the question is, can we describe which points are stable and semi-stable for a reductive group action, and without knowing this invariant ring? So one of the key ideas in Mumford's theory is that, like, determining the invariant ring is a very hard problem. So we most of the time, you know, describing the invariant ring and the invariant is a hopelessly difficult problem. But we don't need that. So that's kind of the idea, is that we can describe a stable and semi-stable locus where this map is defined even without that. And that's the answer for this question, is this Hilbert-Mumford numerical criterion. So this is one source of effectiveness of reductive GIT. So let me just quickly explain. So if you have a T is a maximal torus in G, so we take a maximal torus sitting in G, this reductive group. Then we choose homogeneous coordinates on Pn. So remember, so that this torus action is diagonal, with diagonal weights from alpha 0 to alpha n. So the action is just basically given in this way. We can choose some coordinates on Pn where the action of the torus is a simple form. So the question is, how can we describe, if you just take this projective space as and this action, can we describe a semi-stable locus, stable locus for this torus action first? So, and the answer is very simple. We take these points in the weight space, so this dual of the Lie algebra of the torus, and then we take those of, if you take a point x in your variety x, which sits in Pn, then this point is, let's say, semi-stable. Now what you have to check, you have to collect those alpha i's where the xi is non-zero. You take those weights which correspond to non-zero coordinates. When you collect those weights, you take the convex hull of those weights, and then you check if the origin sits in this convex hull or not. And if it sits in the convex hull, in the closed, including the boundary, then it's a semi-stable point. If it doesn't sit, then it's an unstable point. And if it sits in the interior of this convex hull, then it's a stable point. So there's a very nice geometric description of semi-stability and stability for torus action. Another important thing is that if you take the full torus, G, so this was semi-stability for the torus, for the maximal torus in G. For G, you just have to check if whether any point in the G orbit is semi-stable for the torus or not. So in other words, the semi-stable for the G action is going to be the G sweeps of the semi-stable locus for the torus for any for all G's in G, and the intersection of those. So we'll see that the same picture we hold for a non-reductive GIT for this special class of non-reductive groups I will define soon. So that's Mumford's criteria. So okay, so what happens if the group is non-reductive, right? So that's the next question. So as I mentioned on the first slide, we work and we start with a non-reductive group H, or it can be reductive if you want, but H is a group in a linear algebraic group, which is a semi-direct product of a unipotent radical and the reductive part. And the question is, can we define some sort of, can we mimic the same notions for semi-stability and stability as we in this setup? So we take this coordinate ring. Again, it's generated by A of x. This is a finitely generated algebra. So what are the key problems here? So so one of the first problem people immediately mention is that this invariant ring is not necessarily finitely generated. So, and Nagata gave this famous counterexample this was Hilbert's 14th problem, and the first counterexample given by Nagata from 57, giving an example where this invariant ring is not finitely generated. So this actually already indicates that finding such an example is not easy. So even if you have a non-reductive group, linear algebraic group action on a variety, you have a really good chance that it's actually the invariant ring is finitely generated. So that's not the key problem, by the way, with this theory. So this is a problem, but it's not the key problem. Even if this is finitely generated, the problem is that, another problem is that now then you can take this project of the invariants, right? It's a projective variety because it's finitely generated. So this map is not necessarily surjective. So the image is just a constructible subset in this projective variety. So there's no nice description of like a topological description of the orbit space as we had before. And even more, the topology of the unipotent, like if you just take unipotent groups, right? So let's say we have or any, you can take any linear algebraic group, but in particular, if you take a unipotent group, I show you an example in a second when the group, so the orbit space is messy. So the problem is that is the key invariant is that unipotent orbits cannot necessarily be separated by invariants, right? Even closed orbits cannot be separated. That's a big problem. So here's a very small example. If someone asks you the first non-reductive group you can mention, this is when the first one, right? So C plus sitting in GL2. So this is a embedding of the additive group into GL or SL2. Yeah. Yeah. Where is that?
Oh, generated from all X.
For all X, yeah.
Yeah.
Yeah. Higgs. Well, yeah, that's a good question. So let's talk about action. We just talk about projective varieties, let's say. Yeah. Just complex projective varieties. So yeah, so there's this example here, right? So this is from a paper of Francis Cribb and Brent Doran. So this is a classical example where you have an invariant ring which is finitely generated, but the orbit space is this looks very weird. It shows that this inseparability of closed orbits, right? So you look at this C plus action on the second symmetric power of C2. So let's take the basis y square xy and x square, so correspond to x0, x1, x2. Then we can describe the invariant ring generated by x0 and this one, which is just the equation for the twisted cubing. Sorry, so the curve itself. So x1 square minus x2 x0 x2. And so here's the orbit space structure. So if x0 is non-zero, then this is just a parabola. The orbit is a parabola, right? So you have parabolas actually. When x0 tends to 0, so when you take the x0 equals 0, then for any a, the x1 equals plus minus a they are orbits, right? So the point is that if you take plus a here, a is non-zero, then it's one line. If you take minus a, that's another line. But these two orbits, these two lines cannot be separated by invariant because they kind of limits of these parabolas and they are orbits, right? So any function which takes a value 0 on one should take 0 on the other one as well. So and that's just a tiny little example, but you see that there's this actions and particular actions of unipotent groups on varieties is pretty much ill-behaved and very pathological. But still, one can mimic and try to define open subsets, the stable locus and semi-stable locus, and the geometric quotient and an enveloping quotient, what we call here, in the following way. So I will define what these sets are. So we will define in a second, I will define the semi-stable locus inside X, where so you take X mod H, which is going to be a non-projective constructible subset corresponding to project of invariance, which is now not necessarily finitely generated. Oops. and then this E comes here. Yeah. So, and then in this case, we can define, in a second, I will define the semi-stable locus. I mimic the definition of the semi-stable locus. In this case, it's going to be, again, the map is going to be, it's not surjective anymore, but at least we can define this stable locus fine. And as I said, in this case, there's no topological description of the quotient and no Hilbert-Mumford criterion in general. So how to define this semi-stable locus is, well, we can mimic the definition as follows. We take all non-vanishing subsets for certain f's, functions on X, and the same with S. So this set of functions is denoted by ISS and IS in this case. And we just mimic it, right? So we take those elements in the invariant ring where this affine chart, where non-vanishing set is finitely generated. So the localized ring, when you localize by F, is finitely generated. In other words, the corresponding affine chart behaves like something which we expect a reductive case, so that the invariant ring is finitely generated on that affine chart. So we can patch these together to get this semi-stable locus, right? That's one way of mimicking the reductive GIT and try to define some sort of semi-stable locus in this case. And IS is coming here. It's kind of is the same. So sorry. So it's just SS here. So yeah, like this is a. You take this kind of artificial definition in the sense that we take those F's where the actions for an XF has finite stabilizers, and if you take the quotient of the quotient map, it's a principal U bundle on XF. So kind of the action is nice on this set, right? So that's what the mimic, right? So it's kind of we would like to say that this stable locus is nice because the action on that is automatically a nice action, and we have a quotient. But in this sense, so you can take this subset of X and this subset of X here. So this is semi-stable locus and stable locus. But you can see this is kind of not necessarily useful in the sense in terms of how to determine these. But anyway, we will use this as a starting point to build when we prove the U-hat theorem, or this theorem which I explained today. So we can define these subsets, and then we can define what we call the enveloping quotient as the quotient is this defined semi-stable locus with the quotient H. So it's just as we expect, is the union of the quotients of the patches which you put together. So for each XF, this ring is finitely generated. You take the spec of that, and then you take the union of those. Okay. Now, so the key observation is that, as we have seen, somehow actions of unipotent groups on varieties is really messy. But we can instead, if you add an extra little piece of reductiveness, then they start behaving really well. So, and this extra bit of reductiveness is what we call now graded algebraic groups. So let's assume that you have a unipotent group. So we call it graded if there is a C star acting on the automorphism group of, acting on U, such that the weights of the C star action on the Lie algebra of U are all positive. I will tell you show you examples in a second. So in other words, there is an extension of U. This is called the U hat. This U hat is a C star extension of the unipotent group with positive weights, so that the C star acts with positive weights on the Lie algebra of U. And so we say that this H, which is a linear algebraic group, this is graded. So now we have a unipotent radical and we have a reductive part, right? We say that this is a graded group. This is an internal property. Is that if there is a central C star, which defines a grading on that, a positive grading. So let's see what this means in practice. So we come back to this example of the automorphism group of weighted planes, projective planes. So this is P112. So this is the automorphism group. But you can see that there is a subgroup here of this automorphism group. So I just take C star to be the one parameter subgroup diagonal with diagonal matrices, T squared, T squared, T squared 1, which has this group has positive weights on the generators on this on the Lie algebra of a unipotent radical. So in this case, you can see that the unipotent radical is generated by these 3 parameters in the last column, and the weights under the adjoint action of this C star on them is just 2 minus 1, 2 minus 1, 2 minus 1. So these are 2. So the weights are positive. Yes. Because I want to say this is the I take what's the vector. So I take the action of what is P112. I take the degree homogeneous. So the degree 2 polynomials in P112 and the subspace of that. Yeah. So this is generated. There's a 2 missing. There's a typo here. There's a 2 missing here. So this is just a four-dimensional vector space. With basis is x squared, xy, y squared, and z. Okay. No, not the full. No, not the full. Yeah, yeah. And so, yeah. So that's a very simple example. You see what we mean by that is really. I will give you some other examples on the next 2 slides, but the idea is that you have this diagonal C star which has positive weights on these entries of the matrix. So that's a very general. That's going to be the property. So we say that any group has this with this property that there is this sort of diagonal C star with positive weights on the Lie algebra of the unipotent radical is graded. So I give you 2 more examples which come up. Especially on Wednesday in my third talk, and these are actually the groups which served as the main motivation to come up with this idea of grading, so which we call the reparametrization group. So imagine that you take germs of holomorphic maps from C to Cn. So in other words, you just take polynomials in one variable with vector coefficients. So we take just the first k derivatives of these holomorphic maps, and we assume that the first one is non-zero. So this is really, if you drop this condition, f prime is non-zero, this is just a vector space of dimension n times k. And now there is, we take, whenever you have a map from C to Cn, you can take reparametrizations of this jet. Namely, just take a polynomial reparametrization of C, and that gives you a reparametrization of the holomorphic map. So this is what I know by JK11, following this notation, is the group of K-jets of biholomorphisms from C0 to Z0. So this one acts on JK1n by reparametrization. Again, so you have a map from C to Cn, and you can reparameterize your C, and then this is really an action on this jet. So here is just one can really write down in coordinates. You take a polynomial. This is a jet. This is a holomorphic k-jet of map. So f, which has the first derivative, second derivative, and the k derivative. And then we can take this reparametrization, which is just given by a polynomial in one variable with coefficients alpha 1, alpha 2, alpha k. And then what you do, you just compose these two. That's the action, right? So if you take the composition, we put phi z into z, and then you expand. And so what you get is really this very simple action. You get out of this nice matrix group. This is a reparameterization group, so it's a linear action which has this reparameterization group is a parameterized group, parameterized along the first k rows. In the first row, we have these alpha 1, alpha 2, alpha 3, alpha k, 3 parameters in the first row, and the diagonal C star, as you can see with weights 1, 2, 3 up to k, and some polynomial entries, which in the parameters. So that's the group. This is the reparameterization group. You see that this is a C star, semi-direct product of C star and the unipotent radical UK. Now, it turns out that this specific group, which seems to be this kind of a very innocent example, plays a central role, and it sits in the heart of many deep and geometry problems in animative geometry, and in particular the theory of Hilbert scheme of points. Then it also plays a central role in global singularity theory, sort of determining degeneracy loci for maps, and also play a central role in hyperbolicity questions and hyperbolicity conjectures. So I will mention these examples in my third talk. And then also jets and arc spaces. So it's kind of can be used for in the theory of zeta functions, Iguda zeta functions, and then the monodromy conjecture. So reparameterization of maps is kind of a fundamental thing, and that's kind of the simplest possible incarnation of that, and that's a very important action in geometry. So a third example, which were these non-reductive groups and graded groups. So just want to mention that you see there's this C star in the diagonal, right? So this is already graded subgroup. So it's not just a unipotent subgroup, but there is a C star which gives a positive grading on the Lie algebra. So the Lie algebra now is really, if you put down the Lie algebra of this, it's going to be a nice form. It has also generated by the first row, and it has positive weights 1, 2 up to k minus 1 on the generators of the on the basis of the Lie algebra. So it's a positively graded, it's a graded group as well. And this C star is very important in the theory. So let's see the next general circle of applications of this theory is a construction of unstable moduli spaces. So we have whenever you have a GIT problem, so you have a linear G action on some variety, parameterizing some X, parameterizing some geometric objects, then this moduli space can be, so this parameterizing space can be stratified into locally closed subsets such that all of them, so it's not, the details are not very important, so I probably just drop, but we have a stratification such that the biggest stratum is the semi-stable locus, and then the smaller strata encode you this so-called unstable strata for the GIT problem. And for each unstable strata as beta, it's the important thing for us is that it's really can be described as a if you take the unstable strata, it can be described as there is an associated parabolic subgroup and the variety y beta. So for any beta which kind of indices the unstable strata, there is an S beta and the corresponding Y beta and the parabolic subgroup P beta, such that the action of the original group on S beta can be transferred into an action of the parabolic subgroup on Y beta, and study the problem of the original action on an unstable strata is equivalent to studying this parabolic group action on this y beta. So this means that one can turn if you have a moduli problem, one can turn this problem of describing moduli of unstable objects into a non-reductive GIT problem, where the acting group is a parabolic subgroup. And the parabolic subgroup is always graded. So we can really we can use this to construct a moduli of unstable objects for certain moduli problems. And finally, this is my last example. This example is again it's kind of my my other favorite family of examples, because they play a really important and central role in studying and final resolving of issue of non-reductive GIT blowups, as we will see. So so let's see these groups, which I can call them, these are called regular subgroups of reductive groups, or I can call them like generalized parabolic subgroups. Assume that you have a complex reductive group, let's say GL4, right? So we take GL4. And the subgroup is called regular if it's normalized by a maximal torus of G. So what does it mean? So let's take GL4 to be our group, and take this subgroup, which I just indicate by this diagram here. So this plot here is a subgroup. We take the subgroup of GL4, where the diagonals can be anything, right? Arbitrary. There's no restriction on the diagonals. The lower triangular part is 0. And in the upper triangular part, we put some dots somewhere. And these dots, at these dots, we put 3 parameters, right? In this case, we take A and B. They can be anything. And what we assume that this is a subgroup of GL4. So this actually forces us to make some restrictions on the positions of these dots, right? So it means that if you have an ij dot and you have a jk dot, then you have an ik dot as well. But that's the only thing. So whenever you have this dot arrangement in this upper triangular part, then there's a corresponding subgroup of GL4 or GLN. And this is called Popov-Pomeranian subgroups, or I call them regular subgroups, or we can call them generalized parabolic subgroups. But they definitely form kind of a very simple family of non-reductive subgroups in GLN. And so one of the conjectures is from 1970 still open of Popov and Pomeranian, that the invariant ring for these group actions in GLN is finitely generated. And these subgroups, or these groups, play a central role in Gaussian graphical models in statistics. And as I said, they will come back on my last slide today, if I get there, or if not, then tomorrow, as the leading examples and main motivation for the blow-up procedure, which we have in the end for non-reductive GIT blow-ups. So these are some examples of graded groups in geometry. So now I state the theorem. What's the construction is? So when assume that you have this not an arbitrary linear group, but we have this grading, right? So we have an extra C star, this extra piece of reductive part, which actually will help us in controlling the orbit space. So let U be a graded unipotent group. And this means that we have this U hat, which is the C star extension, which gives you the grading on U. Now we assume that we have an action on an irreducible normal variety X with an ample linearization, so we have a polarized action. So the key point is that we take this what denoted by Z min during my talks. So Z min will stand for those points in X, which is a C star fixed point, and the weight for the C star action is minimal. So there's the C star minimal weight space for the action of X, of C star on X. Now X min is going to be a Bialinski-Birol stratum, so it's going to be those points in X whose limit under the C star action sits in this minimal weight space, right? So So imagine that we have we have only one C star action, we have one-dimensional weight picture, so the weights are just basically points on the line. We take Z mean to be the points which sit over the minimum weight space, and there's this contracting action which actually moves everything towards that weight space. So this X mean is really this is just the flow of the points where the flow of the C star action ends in Z mean. That's an open dense subset of X. So let me state the theorem, and then I will explain some details and also something about the proof. Assume that we have this action. Now it's an irreducible variety with ample linearization L. Now assume that we have this semi-stability equals stability condition. So that means that when we talk about stability equals semi-stability in reductive case, it means that there's no strictly semi-stable points. So in other words, the stabilizers vanish. The G stabilizers vanish on the variety. Now we kind of mimic the same here, but we only focus on the U stabilizers here. So we say that semi-stability equals stability if for every point in this minimal weight space, the U stabilizers are trivial. Then what we do is the following. We have the action on the variety X. We will not change it, but we can always change the linearization of the action by a character. So we can always do that in GIT. And whenever we talk about the linearization of the action, that's or in reductive GIT, the input data is really not just the action of the reductive group in the variety, but it's a linearization, right? And the linearization. The quotient, of course, depends on the linearization as well. So the same happens here. So, and what we would like to say is that let's twist the linearization by a character such that, we have this C star weight picture. It's a one-dimensional picture, so the C star weight sits on a line. We would like to be the origin just above the minimal weight. We can always do that. So we take and then, this is kind of a crucial step. If we would like to form a nice quotient, we would like to take this shift of the linearization. This is what we call well-adapted linearization for the action. Then, if this happens, then the invariant ring is finitely generated. And not just that, but also the enveloping quotient. So what I explained before is going to be the project of the invariants. Kind of that follows from this fact. So, but I mentioned that this is not enough, right? So just because we have finitely generated invariant rings, it doesn't mean that we have a nice orbit space. But in fact, here this happens. So the orbit space is nice. So what we have is that. In this case, the semi-stable locus for the action is equal to the stable locus as I defined before. And this quotient is really a geometric quotient. And moreover, we have a Hilbert-Mumford criteria, which just says that really we have a really nice description of the stable equals semi-stable locus, which is just as before in the reductive case, the intersection of the uses of the C star stable loci. And in this case, we have a very particularly nice description. It's just really, you take this Biaritzky-Birula stratum and you take away the USIP of the Z mean. That's going to be the stable locus. This theorem actually this is what let's say, I just stated here for the U hat action, right? So it's the C star extension of the unipotent radical, but this theorem extends and can be also stated for any graded linear group action. And there is a nice variation of GIT picture when we move not just the linearization, we can change the linearization of the action, but we can also play with the one parameter subgroup, which we use for grading. So they have now two things we can change in the setup. Okay, so that's the theorem. And here I just really give you an example. Like, yeah.
So the condition on the stabilizers of Z min.
Yeah.
I guess also implies stabilizers are trivial in X min. Is that
Yeah.
right? Okay. And
because yeah, that's true. So the limit of the stabilizer sits in the stabilizer of the limit. So therefore the generic stabilizer. So yeah, although I just assume that this for Z min, this means that the generic stabilizer, U stabilizer is trivial. Yeah.
And so for the VGIT picture, if it seems like the quotient is determined by X min and Z min.
Yes. And
So,
but yeah,
it's,
sure.
it's
But
like when you vary the linearization, the X min changes. X min and Z min.
no, the point is that for a given non-reductive group, you can choose your grading C star in different ways. And then if you change the grading, then Z min will change as well.
Okay.
So you can imagine that if the reductive part of the group is not just the C star, but it's let's say a bigger torus, then you can take different grading one parameter subgroups or one-dimensional tori inside that reductive group, and that changes Z min. Once you fixed your grading subgroup, then Z min is fixed as well. That's fine. And then, yeah.
Thank you.
Yeah, so that's the extra piece of, you know, in this toolkit for GIT, for reductive groups, the toolkit contains, you know, the action, that's the action, but also the linearization. Here we have an extra piece of the toolkit, which is not just linearization, but also the choice of the grading subgroup. Okay, this is just a scheme, right? This is just a scheme for example. So this is not very precise. But you see, the Nagata's counterexample for the Hebrews 14 problem was something like this, right? So we have a subgroup of GL32, which has this very simple form. So it's really just we have. If you look at this, this is just a product of additive groups, if you like, because you have 2 times 2 blocks here. But there is an extra twist here is that these T1, T2, T16 are not arbitrary free parameters in this case, but they kind of, well, how to say, they satisfy a free general linear equations. That's the best way to say. So, in other words, they come from a 13-dimensional vector space. So there's always a combination of 13 different numbers so that all of them can be written. So anyway, the point is that according to Nagata's counter, this is the invariant ring is not finitely generated for this group. So this group acts on the 2-dimensional affine space, and the invariant ring is not finitely generated. But the really charming thing, at least I really find this kind of a nice illustration of this theorem, is that if you add these extra C stars, if you add some extra piece into diagonal, which is just really a one-dimensional C star, right? But you have to choose the weights properly. And the only thing you have to think of this as this, or take care of this, that this lower start here, this is a minimal weight, which has a negative weight. And then the weights are increasing, right? So epsilon can be any small rational number, or you can pick it to be 1 in this case. So now this is a small modification, that's a small modification of this group, but if you take this, then the invariant ring is finitely generated. So what does this mean? It just really means when you put this extra C star and you take the invariant ring, it just means really what it means geometrically or algebraically is just, You take the invariant ring here, which is not finally generated, and then you take some graded pieces of that, because, oops, yeah, and then that's going to be finitely generated. So invariant ring here is a subgroup of the subalgebra of the invariant ring here, but it's finitely generated. Yeah, that's right. This was 8 a.m. this morning, sorry. Yeah. Thanks. Yeah, something is wrong, yeah. Yeah, I wanted to do it in pairs, but anyway, yeah. Okay, so I think I have to finish now because time is and it's a good point to stop. So I will not say anything about the proof, but I will go on tomorrow with the situation where semi-stability is not equal to stability, and as like for in the GIT picture, in the reductive GIT picture, then we can make some sort of blow-ups so that get rid of the strictly semi-stable locus, and it was very much unclear until very recently what this general procedure could be for the non-reductive picture, because I will show you that there are very subtle counterexamples for all possible naive candidates for this blow-up procedure. So we finished the theorem with Francis Coben in November, which kind of sets up this general blow-up procedure for the graded case. So I stop here now and then I continue.
Thank you very much. Other questions?
Yeah, hi, thanks for the talk. So can you comment a bit, or maybe you're going to say this tomorrow, I don't know, but can you comment on, say in the case of quiver representations, let's say you're constructing moduli of quiver representations or moduli of Bridgeland stable objects or something like that, then there is, if you look at a polystable object, you can, sorry, semi-stable object, you can have further refinements to the Harder-Nussbaum filtration, which can be formulated using GIT. Can you just comment on how this framework applies to that situation?
Yeah, so one of the main obstructions for using this theory in this massive classical examples is if you write down, so that's what actually we talk about, is that I stated this theorem for when the semi-stable equals stability, and it doesn't hold in these applications. And somehow the blow-up procedure can be very complicated. There is a blow-up procedure, but it really makes the picture very messy. It kind of happens in reductive cases as well, but this happens here as well. So, and that happens with quivers as well. So that's one of the main problems.
Are there more questions? Are there more questions?
So for example, say you have an action of a non-reductive group, just like you have told us, and you define the semi-stable locus as above. How is it related, that semi-stable locus, for, say, if you only take the restriction of the action to the maximal reductive subgroup?
Yes, so
related, yeah.
Yes, so the construction in general works in stages, as you are suggesting. So we take, if you take an arbitrary H, I did not explain that, right? So I take an arbitrary H, then it normally has, if it's a C star, it has it is just a C star extension of its unipotent radical, then this is the theorem, right? So we can do that. And if it's not, then you do the quotienting in two stages. You first quotient by the C star extension, and then you quotient by the residual reductive group action. Because you can form this quotient, and then there is an induced action of the residual reductive group on the quotient, and then that's just ordinary GIT, like reductive GIT for the rest. But in practice, this can be a bit tricky. This means that this assumes that you can describe this quotient, this U-hat quotient, right? And you can describe the residual action on.
Thank you.
Thank you.